Let's go ahead and graph example 2, and we're going to see if we can look at the graph and find the derivative of f. The graph is defined to be x squared plus 1 for any x that's less than 1. So let's go ahead and take 1 and plug it in there. When x equals to 1, we plug that in there, we're going to get 2. And because the graph is not defined at 1, we use an open circle. Now notice that this is a quadratic function, and the quadratic function has a vertex that supposedly is at the origin, but now it got shifted up 1 unit. So the function is going to look like this, like that. All right, there you go. So we graph this part. Let's go ahead and graph this part. Now this is just a linear function. It's just a line, and it's defined at x equals to 1 and on. So when we plug 1 in there, we get 2. So when x equals to 1, the output is 2, which means that we're able to fill in that hole. Let's pick another point. Let's pick the point x equals to 2. When you pick x equals to 2, plug it in, you get 4. So 1, 2, 3, 4. Now we can kind of connect these 2 points, and we're able to graph the function, this piecewise function. Now the question here is, can we determine by looking at the graph whether or not f is differentiable at x equals to 1? And by looking at this graph, we notice that the graph is really smooth. There's no corner here, it's really smooth at x equals to 1. So yes, it is differentiable at x equals to 1. Were we able to do that by looking at the graph? Looking at the graph, it seems like it is smooth, but we would not know for sure. For sure, I cannot say that the function is differentiable at x equals to 1 because I don't know for sure that it is smooth, even though it looks like it is. Okay. If that's the case, then how do we know whether or not the function is differentiable at x equals to 1? Well, to answer that question, we have to go through some Huddle tests. Now, this data here, or this summary here, tells us a method to determine whether or not we include the boundary point as within our derivative function. So here's what we know. When given a function, when given a piecewise function, then the derivative of the piecewise function is just the derivative of each one of these parts separately. And we either don't include the boundary, you see how the equal sign wasn't included, or we include the boundary. Now, how do we know when to include the boundary and when to remove the boundary? Well, if you're able to look at the graph and see the obvious, which is the corner, then don't include the boundary point. See, because derivative at a corner does not exist. But a lot of times we're unable to tell because this one looks smooth. This one looks smooth. And if it looks really smooth, then hey, the derivative function should include the boundary point. To make things easier for us, okay, here's what we need to check. To decide which one of these, we must determine if y is differentiable at exactly x equals to a. And the way how we determine that is we look back at the original function, and we need to make sure that the original function is continuous at x equals to a In the first two examples, both of those functions were continuous at x equals to a. And we also need to check for continuity of the function y prime at x equals to a. And if both of these conditions are satisfied, then we include the endpoints. Let me show you how easy it is to determine whether or not we should include the endpoints. So here is my piecewise function. I want to find the derivative function. All right. So y prime, according to this differentiability summary, I know that y prime of my piecewise function can be found by taking the derivative of each one of these pieces separately. So for the first piece, it is 2x, okay? And then for now, I'm not going to include the boundary, okay? I'm gonna take the derivative of cosine, which is negative sine. Okay? And for now, I'm not gonna include the boundary. Obviously, I'm not gonna include the boundary because this one starts without the boundary. Now, to decide whether or not to include 0 in our derivative, we have to check these two conditions. Check for continuity of the original function at x equals to a. Our a here is just where the boundary is. So our a here is like we're checking for continuity at x equals to 0. What does that mean? Well, if I were to plug 0 into the first piece, does that equal to the same value as plugging 0 into the second piece? If I plug 0 into this first piece right here, I'm gonna get 1, okay? And if I plug 0 into my cosine function here, cosine of 0 is also 1. So guess what? I concluded, or we can conclude, that the original function is continuous at 0 because it takes on the same value, okay? Now, we also need to check for continuity of the derivative function. So I am gonna replace 0 into each one of these pieces and see if I get the same answer. For the first function, which is 2x, when I plug 0 in there, I get 0. Okay. For the second function, which is negative sine of x, guess what? When I plug 0 in for sine of x, I also get 0. So at the boundary point, the original function is continuous at the boundary point, and so is my new derivative function. It is also continuous at the boundary point because it equals to the same value. So therefore, we need to go back and we need to include the boundary point. We need to go, oh, that should be a greater than or equal to. That's the whole purpose of this lesson, which is to decide whether or not to include the boundary point within your derivative function or not. Let's go ahead and do a last example here. Find the coefficient a and b so that the function, this function, is differentiable. There are two stages to this problem. First, we know that in order for this function to be differentiable everywhere, we just have to worry about the boundary point. And to take care of the boundary point, we need to make sure that the function is continuous at the boundary point. The derivative function is also continuous at the boundary point. So for now, let's take care of continuity at x equals to 1, because that's the boundary for the function f of x. Remember that f of x has two pieces. In order for us to make them continuous, we need both of them to be equal to each other when x equals to 1. So here's what we know. We want this to be equal to this when x equals to 1. When x equals to 1. So we replace 1 in here and we get a minus b is equal to 1 when I replace 1 in there. So that's the first stage. The second stage is we need to go ahead and take the derivative of this function, which I'll write it up here if you don't mind. which is going to be 2ax. The derivative of b is going to be 0. The derivative of the bottom guy is going to be 2. So we took the derivative of that. And we also want them to be equal to each other at x equals to 1. So we check for continuity at x equals to 1 for the derivative function. Go ahead and set them equal to each other and replace x equals to 1 in there. That is going to give us 2a equals to 2. So we know that a equals to 1. We're trying to find a and b so that this function is differentiable. So when a equals to 1, these two functions are guaranteed to be continuous. But we also need to find that b value, right? We know how to find b because we have a relationship between a and b and this number 1. So if you know a equals to 1, replace a with 1 and solve for b. So if you do that correctly, it's going to turn out that b equals to 0. So guess what? We answered this question already. We found coefficients a and b that makes this function differentiable. If a equals to 1 and b equals to 0, this function is guaranteed to be continuous, and so its derivative is also guaranteed to be continuous when a equals to 1 and b equals to 0, which satisfies these two conditions. And that means that the function is differentiable at the boundary, which means it's differentiable everywhere, because the only place that it is not differentiable is at the boundary. But we just fixed this a and b value so that it's differentiable at the boundary.